Hi there. This video is on integration by substitution, a review of something that many people have seen in Calculus 1. Tends to be at the end of that course, and it is a bit tricky, so I'm going to run you through how to do it. And I have some problems prepared for here, approximately 4 problems, and they do get more complicated as we go on. So if you are familiar with integration by substitution, you can jump to the third or fourth problem to see how these can get more complicated. All right, so first of all, let me kind of give a clarification of integration by substitution. It's really misnamed. What it should be called really is simplification by substitution. We aren't really integrating anything by using substitution. Simplification. All we're doing is we're using this technique of substitution to simplify this formula so then we can use our normal antiderivative formulas. There's no new formulas we're going to be using. We're just going to be using this method of simplification. It involves a bit of algebra, and what we get out of it should be a much simpler problem, which we can use our normal antiderivative formulas to find. In fact, all of the different integration techniques that we learn in Calculus 2 all are really simplification techniques. There are no new formulas for integrals or anti-differentiation, but there are some more sophisticated ways of simplifying these problems so that we can use our typical and normal antiderivative formulas. All right, with that disclaimer, let's get into some examples. So my first example, it's a basic example right here. We have this integral, it's a fraction, and we're going to use substitution to do this. The way substitution does simplifies this is we're going to let a variable represent some portion of this integral problem. And we typically try to find the more complicated part. With fractions, the denominator is typically more complicated, and certainly dividing by two things is very complicated, much easier to divide by one thing. So we're going to take this part down here, and we're going to make that equal to u. So essentially what we have now is an integral. We have x squared divided by u dx. We've replaced x squared minus 8 by u. The situation now is that we have two different variables. We have x's and u's, and we have dx, and there's no integral formula that has multiple variables, at least at this level. Of course, when you get into Calc 3, there are definitely some situations where you can anti-differentiate multiple variables, but we are far from there. So we'll need to continue to simplify this so there's only one variable. And the idea is we want our new variable u. We don't want to go back to our old variable x. We already know what the thing is in terms of x's. It's the thing we didn't know how to do. We wanted to simplify. So we're going to get rid of all these u's. Right, so how are we going to do this? Well, the first thing we're going to get rid of is the dx. The dx is very important to convert into a du. So how do we do that? Well, dx is the differential of x, which has to do with the derivative of x, the change in x. And we can use our derivative calculations on our substitution on this thing right here to find the derivative. If this were y, we would call it dy dx, but it's u. So the derivative is called du dx. Notice we can't really use y prime. We have to write du dx because we're going to solve for dx. I'm going to multiply both sides by dx. So this becomes du is equal to x cubed minus 8 dx. And then I'll divide by the, okay, let me try this again. I don't want to start the video again because I want you to see that some people make mistakes. I wrote du dx, but I never differentiate the right-hand side. I have to differentiate both sides, my friends. I have to differentiate this side here with respect to x, and I had to differentiate this side with respect to x, and for some reason I didn't even do it. So let me differentiate x cubed minus 8 with respect to x. The derivative of x cubed is 3x squared, and the derivative of minus 8 is 0. All right, so let me correct this properly. So I get du is equal to 3x squared times dx when I multiply both sides by dx. And if I solve for dx, I get du divided by 3x squared. Okay, I corrected my mistake. So now I know what dx is. Dx is this thing right here. And so I can now know how to substitute in for dx. All right, so let's go ahead and do that. X squared over u, and dx is our du over 3x squared. All right, now, as it turns out, we get some additional simplifications. So there's an x squared here on the denominator, x squared on the numerator. X squared divided by x squared is 1. So they essentially don't do anything. 1 times anything is still the thing. So some people will say it cancels out, but it really divides to equal 1. So we don't have to write it anymore. So on the top, we have a du. On the bottom, we have a 3u. Some people will like to write this with the 3 on the outside. It is in the denominator, so if you do choose to write it on the outside, remember it has to remain in the denominator, so like a 1/3. And then we have du over u. So the question is this new formula simpler than the original formula? The original formula was x squared over x cubed minus 8. Has some x's on the top, squares on the top, cubes on the bottom. Now we just have a u. In fact, we can write this as 1/3 u to the -1 du. So no fraction at all. And the antiderivative of u to the -1 is one of our formulas. It's one of our antiderivative shortcut formulas. Looks like it's right here, number 5. 1 over x is the same as x to the -1. And the antiderivative of x to the -1, or 1 over x, is the natural log of the absolute value of x plus c. These formulas work whether they're x's or u's or thetas. It's just a variable there. As long as the variable in the function matches the variable in the differential, then we get this answer right here. All right, so this right here is going to equal 1/3 natural log of the absolute value of u plus c. Now we're not quite done. Even though we did find the antiderivative using the formula, we have written our answer in a variable which wasn't part of the problem. The problem itself had no u's in it. U was our invention to help us simplify this thing. So to get the correct answer, you're going to have to put it back in terms of the variable that the problem was given it, which means you're going to have to put it back in terms of x. That's a lot easier than it sounds. Yes, it's a lot easier than it sounds because we know what u is equal to. We define u as x cubed minus 8. So we can simply write this as 1/3 natural log, not of u, but of x cubed minus 8 plus c. And that is the first example problem of simplifying using this method of substitution. All right, for the second problem I have, it's virtually the same as the first problem, but it's upside down. In other words, instead of x squared on the top and x cubed minus 8 on the bottom, I have x cubed minus 8 on the top and x squared on the bottom. All right, so I did this problem sort of next to the other one to kind of make a couple of points. So I'm going to start off in our typical fashion with using a u substitution to try to simplify this thing. Again, we want to choose a more complicated part. There are different things to choose. They're all going to kind of work out the same way. I don't want to do 3 different ways to show you the different results. I'm just going to choose what I think is most people's choice, which is this top part, the more complicated part. So we're going to let u is equal to x cubed minus 8. That gives our integral here as u over x squared dx. We're going to have to convert everything into u, so we're going to have to get rid of all the x's. Dx is the most important thing to get rid of. So I'll differentiate this thing du dx. We already know what that is from our previous problem. It's 3x squared. And we also know how to solve for dx in our previous problem. Whoops. I'm going to do it down here. Dx is equal to du over 3x squared. So I'm just going to take that version of dx, and I'm going to put it into my formula. Dx is du over, that should be a u, du over 3x squared. Again, we have this 3 in the bottom, so we can take that out as a 1/3 if you want the constant not with the rest of the formula. We have x squared times x squared in the denominator. We have u times du in the numerator. So we have u du over x to the 4th. So the x's did not simplify, at least not in a way we were hoping. They didn't quote unquote cancel. They became x to the 4th. Well, that certainly wasn't promising as we hoped. And we still have not converted all of the x's into u's. We still need to convert all of the x's into the u's, even this x to the 4th on the denominator. So how do we do that? Well, again, we defined what u is. We know this because we made up that exchange, that substitution for x's into u's. So we can simply solve for x in this problem. If I add 8 to both sides, I get u plus 8 is equal to x cubed. And if I cube root both sides, I get x is equal to the cube root of u plus 8. Or maybe we should write this as u plus 8 to the 1/3 exponent. So now I know how to get rid of x. So I'm going to take this, and I'm going to put it in for the x over here. All right, so what does that give us? So that gives us 1/3 integral u over u plus 8 to the 1/3 to the 4th, which is the 4/3 power, right? You could write that as 4/3 if you wanted to, times du. We could put the du over here. Maybe that makes it look a little easier. So now that we have everything in terms of u's, we're going to ask ourselves, is this simpler? And the original problem up here had x cubed minus 8 over x squared. And our new formula has u over u plus 8 to the 4/3. I don't think it got simpler. Remember, the whole purpose of this is to get it to be simpler. And this technique did not result in that. One of the things I wanted to show you is that u substitution, this method of simplification by substitution, is not a panacea. It does not always work. Even if you chose a different version of u in this problem, it's not going to work. Even though it looks a lot like the first problem, which did work quite nicely using substitution, this one does not simplify using substitution. So one of the reasons I chose this problem is to show that even though things look similar, they don't necessarily always use the same technique. The second thing I wanted to explain to you is that we don't need to use any complicated simplifications at all because we know algebra. And dividing by two things is very, very different than dividing by one thing. Dividing by one thing is called the distributive property. It's like by multiplying by one thing, that's called the distributive property. Dividing by one thing is also called the distributive property. So if I distribute or divide by each of these things, what I get here is the antiderivative of x cubed over x squared minus 8 over x squared dx. And I'll use some more algebra to simplify this. X cubed over x squared is x. And I can write that as x dx. I could do this separately. And the the simplification 8 over x squared is just 8x to the minus 2 because negative exponents. And now we have two problems which are just powers, x to the 1 and x to the minus 2. And so we can antidifferentiate those directly without using any kinds of fancy things like substitution. The antiderivative of just x is 1/2 x squared. We do need a plus c, so I'll just put it over here. And the second part is a minus, and the antiderivative of x to the minus 2. Leave the 8 here by itself because it's a constant being multiplied. I have to add 1 to the exponent. So it's not minus 3 because that would be subtracting 1. It's actually minus 1 because I add 1 to the exponent and I divide by that same thing. Little simplification I can do here. So I get 1/2 x squared or x squared over 2. The minus 8 divided by minus 1 is positive. 8x to the minus 1, which you could also write as 8 over x, and then plus c. And so that is the correct antiderivative for example B. All right, so hopefully that didn't seem too tricky. I just wanted to kind of get a couple of points across for a problem that ultimately didn't use substitution as a method to simplify. All right, last two problems, I promise, are indeed substitution problems. So let's go ahead and look at those. They are getting more and more complicated. So C and then D, we're going to be both simplified using substitution, and you hopefully will see how these problems get more and more complicated using the algebra techniques. All right, in part C, we have the antiderivative of x times sine x squared times e to the cosine x squared. There's lots of things that you can possibly use to try to simplify using this method of substitution. So what to choose? Well, we can choose maybe u is equal to this thing right here, sine x squared. Maybe we can let u be e to the cosine x squared. It's not going to be clear what to use. And when using this technique, you should sort of get into the mindset that you're not always going to choose the best thing or the thing that works each time as your first guess. How do you know your first guess doesn't work? Well, you're going to get something that doesn't simplify. Remember, we chose something here that didn't work, and what we got as a result was much more complicated than what we started with. So we know that that didn't work. So if you try a substitution and it doesn't get simpler, then you're going to say, okay, either I need to choose a different substitution, or maybe the substitution isn't a method that works for this type of problem. All right, so I'm not going to do the problem anyways. If you want to see me do it a different way, you certainly can log on to Zoom hours or email me. But the best substitution for you here is cosine x squared. It's this thing in the numerator here. It's definitely it's thing in the exponent there. It's definitely a complicated part of the expression, but it doesn't grab too much. It doesn't make too much of equal to u. So when we differentiate it, we don't get too complicated a result for du dx. There's got to be some sort of balancing between simplifying this thing and not making it much more complicated when we have to solve for a dx. So this is the one that's going to work. Again, give things a try as you're doing these problems, so you get used to maybe trying to guess something that works pretty consistently, either your first, second, or third choice. All right, so let's go put this u in here. So I have the antiderivative x sine x squared. E to this whole thing up there is u now, and then dx. I'm going to have to find the derivative in order to solve for dx. The derivative of cosine x squared, it's a derivative. Derivatives means we can use the derivative shortcut formulas. This derivative is a chain rule. It's cosine of an inside function. So we're going to have to use the chain rule to differentiate cosine of x squared. The derivative of cosine is minus sine. And then I have to chain by differentiating the inside function. So that's the derivative. And then I can solve for dx. That would be du. I'll smush the -2 and the negative and the 2 together. And here's an x, and here's a sine x squared. So now I know what to put in for dx. All right, let me write this out. X sine x squared e to the u. And my dx is this crazy thing right here, du over -2x sine x squared. And now we get something that looks more hopeful. We do get some divisions here, x divided by x, and sine x squared divided by sine x squared. Those all divide equal 1. And so what are we left with? We're left with e to the u, du. On the bottom, we have just -2. -2 is a constant, so we can even write this on the outside. Remember, it's in the denominator, so make sure you keep it there. And then we have our, let me try to make this look a little nicer. We have our simplified integral. Is this simpler than what we started with? What we started with was this thing up here with x sine x squared, e to the cosine x squared. And what we have now is much simpler. It's just e to the u. And e to the u is one of our shortcut formulas. The antiderivative of e to the u is itself. The derivative of e to the u is e to the u. The antiderivative of e to the u is e to the u. e to the u is the only function, or e to the x is the only function whose derivative is itself. Okay, so this is going to equal -1/2 e to the u plus c. Once again, we need to have our answer in terms of the variables that are given in the problem. We can't just use some made-up variable that we invented to help us simplify this problem. So we are going to have to put it back in terms of x's, but that's easy because we invented what the relationship between u and x was. We said u is equal to cosine x squared. So that means this problem right here can be sort of re-simplified back as e to the cosine x squared. Instead of u, we're going to write the version of u, which is cosine x squared plus c. And that is your answer to part C. All right, one last problem to do. And it is hopefully something that you're getting used to how it works. Maybe you give it a try on your own. It is more complicated than C. So if you give it a try, don't worry if you get stuck. I will show you why this, in my opinion, is more complicated than the previous problem, even though it does use the same technique. All right, so what's complicated here? What do we want to make as u? Well, we're going to make this inside part be u. You could actually make u be the whole square root. That's not a horrible choice. It does end up with a lot more algebra, but it does end up ultimately simplifying in a similar way. I'm just going to choose the one that makes it a little easier for me to explain just by doing the stuff inside the square root. So I'm going to let u be 3 minus x. When I have the square root of two things, there's not really a good way of simplifying it. I can't really square each thing separately. There's no distributive property with the outside and the inside. You know, it just doesn't really simplify very well. When you have two things on the inside, it's just not nice. So we're going to take those two things, 3 minus x, and write them as a single variable. And that means that our equation now is x square root of u dx. So again, instead of just two things that I have to worry about under the square root, I have one thing, much easier. In fact, we can write this as x u to the 1/2, right? We don't have to write the square root symbol. We can write this just using our normal numbers. So that's our formula we have to differentiate. Once again, we have too many variables. Oops, someone may have noticed my mistake. I think I'm getting a little bit tired, but instead of writing dx, I wrote du by accident. So again, I don't want to erase things. I just want to show you that everyone's human. We all make little mistakes. The thing is to go slow enough and methodically so you can catch those mistakes and correct them. So I corrected my dx. It still is dx. I haven't made any substitutions for dx in terms of du. So it still has to be a dx there. The only thing I wrote was u is equal to 3 minus x. So that's the simplification part. But you probably know the routine by now. I have to get rid of the dx part. And the way I'm going to do that is by differentiating. Let me go back to green. So the derivative of u is called du dx. And the derivative of 3 is 0. The derivative of negative x is -1. So I can solve for dx. Dx is equal to du over -1, or just negative du if you want to write it in a simpler way. So we're going to take this version of dx and put it into our problem. X u to the 1/2. And then we get du over -1. I'm just going to move the -1 outside. So it's 1 over -1, which is the same thing as -1. I don't need a fraction anymore, but I'll write it this way temporarily so you can kind of see what's going on there. All right, so I successfully got rid of that 3 minus x part. I wrote it as u. I got rid of the dx part. I wrote it in terms of du with some number going on the outside. But I still have not converted everything into x's. There's no like cancellations or divisions that get sort of the x here. I just had a -1, which does not simplify with x. It just got brought out. So I still am not ready to try to anti-differentiate this because I still have not completed my conversion, my substitution into u's. I got this x thing I need to worry about. So how to get rid of the x thing? Well, if you've been watching the previous problems that I've been showing on this video, you might have a hint. Remember, we are in control of what u is. We wrote u is equal to 3 minus x. That is our writing. We invented this u thing. We know how to convert between u's and x's. So we can use that to convert anything. So in this particular problem, we can just solve for x. So I'll write this over here. Move myself a little bit, I guess. So I'll just write it without doing anything yet. I'm gonna maybe subtract 3 on both sides. And divide by -1. Or multiply by -1, whichever you want. So hopefully you can follow that basic algebra where I'm solving for x. And that goes in for x. All right, so we have -1. Negative 1 over 1 is 1 over -1 is 1. Instead of x, we have u plus 3. And we have u to the 1/2 du. And now we have successfully converted all of these x's into u's. And now the question is this simpler? It doesn't necessarily look much simpler if you look at the top thing, x square root 3 minus x. The u is kind of the square root of u, so there's still a square root in here. The big difference is instead of having 2 things under the square root, we only have 1 thing under the square root. The only thing under the square root is the u. And so we can now use the distributive property and multiply this out. So I can multiply this times this and multiply this times this. If I have something on the outside, multiplied by parentheses with one or more things added together, I can distribute. So this is u to the first power times u to the 1/2. If the powers have the same base, I can add the exponents. So I get negative u, pen is failing me a little bit, negative u to the 1 plus 1/2 is 3/2. And then I get plus 3. Well, that's just 3u to the 1/2 because 3 times that thing is just that thing. And then I get a du. And each of these can be anti-differentiated just using the normal power rule, right? Because they're added together, I can do them separately. All right. Almost done with this problem and almost done with this video. All right, so we get -1. I get the antiderivative of negative u to the 3/2. Negative is a number, so it will not affect the antiderivative. To antidifferentiate u to the 3/2, I'm going to add 1 to the exponent. And I'm going to divide by that same exponent. And then over here, the 3 is unaffected by antidifferentiation. Add 1 to the exponent, divide by that same new exponent value. And I do need a plus c at the end. Last thing I do is just kind of simplify things, make things look a little bit less messy. And so my final answer, I get a negative times a negative is a positive. I can reciprocal the 2/5 or the 5/2 to 2/5. So 2/5 u to the 5/2. Here, I'm going to keep the 3 here and reciprocal the 3/2 to be 2/3. So 3 times 2/3. It looks like the 3's divide out to equal 1. And I get u to the 3/2. And then I get plus c. I did forget the minus. If you did notice, I have to do minus this and minus this. And I forgot to do the second minus. That's kind of sloppy on my part. I need to be a little more careful about like distributing correctly. So there should be a minus here because -1 times plus 3 is -3. I still flip the 3/2 to 2/3. So anyway, I did catch it, even though I did mess up a little bit at first. But like I said, just go slow enough so that you can catch those kinds of little mistakes that we all make. Once again, we have one more step, which is to put things back in terms of our original variable, which was x. Our original variable is all the way back here. U is equal to 3 minus x. I'll write it down here just so we have it handy. But that's our invention of what u was. It's 3 minus x. So I just pop that back into our answer, and then we're done with this last example. So what's my final answer? My final answer is 2/5. Instead of u, I'm going to write 3 minus x to the 5/2 exponent. Minus 3 times 2 over 3 is just -2. And then I get u to the 3/2. plus c, and that is the antiderivative of this problem in part D, which was the square root thing. Its answer is pretty complicated. The question didn't look that complicated, but in order to do this, we had to use some very complicated algebra to substitute for u's and substitute for du's and substitute for x's, and we eventually got this answer at the end. All right, so hopefully this video was helpful for you to understand the technique for integration by substitution or simplification by substitution. Please reach out if you would like some more practice or have questions with anything else. And I hope you have an enjoyable day.